a bit about analytic continuation. This meeting is okay. So yeah, to understand the analytic continuation of zeta, let's see what zeta does to the lines in the complex plane. So it takes the line from 1 to infinity, like a real line from 1 to infinity. It takes it to itself. So it's kind of invariant for it. Then imagine you shift the line to the imaginary particle to +1, imaginary particle to -1. What happens to that at infinity? Everything goes back to 1. And I have a picture to show you. So this 2 yellow line would indicate the line that I was talking about, the imaginary part being equal to +i and -i. And the rest of the green is like a less highlight. But let's see what it does, zeta function, the formal definition, what it does to these lines. So it goes to the yellow line, you can see it from here, goes to something like this. The analytic continuation means that I continue this picture to the right side in a differentiable way. So it's like this yellow lines here should go something like kind of in a differentiable way. You want to extend these curves, the rest of the grid. So something like this you want to have in mind. So that's what we mean by analytic continuation, and it's unique. So now that I have a zeta like well-defined on whole complex plane, so these are my explanation of what analytic continuation kind of means. It's means that you want to preserve these angles. So between the grids you have 0 and you have a 90 degree, and in the extension you want to preserve this angle. And one important point is this analytic continuation is unique. It's you cannot have it two different. When you extend the definition, you cannot have 2 different definitions, just unique. And this is important is because arithmetic exists in the real of s bigger than 1. So that you have the connection with the primes there. When the definition comes from real of s smaller than 1, everything disappears in terms of how we connect this function to prime numbers. But since the analytic continuation is unique, the property is kind of contagious to the whole complex plane. So one fact that I'm using from arithmetic is that integers, they have unique factorizations. And I already mentioned that zeros of the Riemann zeta function are very important. Basically, one application is the distribution of prime numbers. So because integers, they have unique factorization, we can write an Euler product for the zeta function, this product here. This basically means if I take the log, and the log is a very good tool to look at the zeros of functions. So basically I can take a log of this function and I will have a nice series expansion for the log. Right here, log when s is close to a 0 of the Riemann zeta function, log jumps, and therefore this sum over p to the power minus s should also get bigger. So people who this is a comment, people who take a probabilistic approach to studying the zeros of Riemann zeta function, what they do, they look at p to the power it as a independent random variable that is uniformly distributed on the unit circle. And some of independent random variable, uniformly distributed, you call it IID. Some of them, they have what's known as a normal distribution because of the central limit theorem. So we expect this to behave like a normal distribution. And this is, Selberg has a theorem called the Selberg central limit theorem, basically proving this observation. As I mentioned, logarithm is, we look at the logarithm because logarithm is a very good tool that you can study zeros of a function. And because of the Euler product, it gives us a good good sense of how the logarithm look like. And I'm repeating this point that the Euler product exists outside of, like in real Fs bigger than 1, but the properties uniquely would extend to the whole complex plane. So one way of like looking at it is from the functional equation of the Riemann zeta functions. As you can see, in a simple way, I can write zeta as some understandable function times zeta of 1 minus s. And so when you know zeta s for real Fs bigger than 1, basically you know the zeta s for real Fs smaller than 0. There's a little bit of problem is that the whole mystery falls in the real Fs between 0 and 1, and that's called critical strip. And the problem with the functional equation we have is that it takes where the mystery is to to itself. So it doesn't give so much, like around, like when S is like real Fs is around 1, it goes to real Fs around 0. Imagine real Fs is called a 3/4, it goes to real Fs equal to 1/4. And so that's a little bit of problem with it. For technical reason, instead of working with log, we work with logarithmic derivative. It just makes everything nicer, the formula. And the logarithmic derivative has this series expansion. It's basically supported on primes. Lambda of n is equal to log of p when you hit the prime or prime power. It's like a weighted indicator function of primes. So the functional equation also translates here to the logarithmic derivative in this way. And if I want to bring the zeros completely to the picture, connected to the primes, what I do, I integrate the logarithmic derivative, x to the power s divided by s, and poles, basically zeros of the zeta are going to be poles of this function. And I end up with what's called the explicit formula. And I just put the important parts, 3 points. So there are like other elements in this formula, but they're not as they don't play as much role of this, as important of x and so x to the power rho divided by rho. The x is what we expect of this function look like. So sum of the lambda and from n smaller than x, we expect it to be around x. And this guy takes care of the error term from the expected value. Small comments that the original formula that Riemann had was a bit different than this. He had, instead of lambda, I think he had 1, because that goes back to the problem of Gauss. I'm gonna explain it later. So this was like Gauss was very interested in this problem to find how many prime number exists smaller than x, and his prediction was that it's around x divided by log x. He was working on this problem. He was unable to solve it. This equivalent form of this would be sum over lambda. I was weighted indicator function primes about asymptotically about x. And there's Euler worked a bit. Euler had the Euler product. He used it to prove that there are infinitely many primes. There are other ways to prove that, very easy ways to prove there are infinitely many primes. From what I know is that Riemann, he read Euler's work, and since he had this vision on complex numbers, he came up with the analytic continuation of zeta function. He found a functional equation, the explicit formula, and he also calculated a bunch of zeros. He does calculate a bunch of first zeros by hand. So this is from his notes that they preserve in the library in Göttingen. I picked this page because he calculates, like by hands, he's calculating a bunch of zeros. Let me go back to logarithmic derivative. So I'm going to explain that why we can prove what's known as prime number theorem. Prime number theorem is equivalent to what Gauss was trying to prove. So why we can prove prime number theorem, but why we cannot like do more, like say anything more. So if you look at the series expansion of the logarithmic derivative, And as I say, this is basically supported on primes. And I say p to the power it, which would be e to the power log p it, they behave like a independent random variables. In a way, you can look at them as a random walk. If the prime number theorem, the theorem the Gauss was trying to prove, is incorrect, say, so then the number of primes smaller than x is not x divided by log x, then this is equivalent to have a Riemann zeta function having a 0 at the line real of s equal to 1. If you get a 0 there, that violates the prime number theorem. So basically, why we can prove prime number theorem is that if there's a 0 on one line, almost all of this, like e to the power minus it times log p, for almost all of these primes, they're going to be equal to 1. Which, look at it, you can look at it this way. You have random walk, is all the step upward. It's very specific. It doesn't give you so much wiggle room. In other words, it just imposes such a strong property that we can use that as strong property to create a contradiction. But if, imagine there's a 0, 0 is not on the line, a little bit shift, like inside the critical strip, then this property falls apart. Then basically you can say, when I sum this e to the power it log p over primes, I get a little bit of cancellation, but it's not, you don't have such a strong property that all of them are almost equal to 1. So then from there, you cannot, this whole, the trick we use to prove the prime number theorem falls apart. It's no use anymore, because like they can half of them be equal to 1, half of them minus 1, whatever. Like it can be like equal distributed around a unit circle. Maybe it gives a little bit of edge toward 1, but that doesn't help you, or we haven't found a nice way to use it to prove that, to create a contradiction. Again, stuck. Can I go to the next slide? Oh, what? Anyway, like if I want to sum it up, summarize it, having a 0 on real of s equal to 1 imposes a very strong structure on this sequence e to the power it log p, which normally in other circumstances you don't have it. So let me go back to explicit formula. I want to make a point here. This is the explicit formula. Take x be a little bit smaller than a prime number, and then increase it slightly to include that prime. So x goes from p minus epsilon to p plus epsilon. This right-hand side and this left-hand side, it jumps by log of p. In the right-hand side, x does not change much. So it goes from like p minus epsilon to p plus epsilon. But so therefore I have the jump, this term here, this captures the jump of log p. One way of looking at it is like if you sum x over 0 of Riemann zeta function, and x is very close to a logarithm of the prime number, or x close to prime number, then you see a like a kind of a jump in this sum. What I'm trying to say is much more nicely is captured in what's called the Landau-Gunek formula. And Landau proved the following, that you can write the indicator function of primes in terms of the variable here to the power of zeros of the Riemann zeta functions, like an average of them. And so it's like an arithmetic function you have, indicator function of primes, you can nicely write it as x to the power rho. Also, Gunek worked on this formula. He works, as you can see, I don't have the dependency on x in the error term. What Gunek does is that he worked this out, and you see that the error term now depends on x. So it's more uniform version of it. But the important point is that it's a nice way of seeing how primes are related to the zeros. And you can write the indicator function of prime, basically, weighted indicator function of primes in terms of the variable to the power of zeros of Riemann zeta function. It's if this is a bit strange, like keep in mind we do this thing in mathematics a lot. Like, for example, when you write Taylor series for a function, you write the function in terms of its variables to the power of integers with a certain coefficients. Or when you write it for expansion, you do the same, and you write a function in terms of integer powers of e to the power I t. And there's a difference here, though, with the formula I showed. That I'm trying to say, like, oh, how can we write an arithmetic function in terms of the variable to the power of zeros of Riemann zeta function? One big difference is that in both of these cases, we have a very nice algorithm to find these coefficients here. Like, what would be coefficients of this? So x to the power n in Taylor series, that kind of act like a base for the space of functions. And we have a nice, like, very concrete algorithm to find, and we know what kind of functions we can do that. We can write in terms of this expansions. It's not clear, though, this thing. If I assume that x to the power rows kind of act like a base or part of a base, it's not very clear how you can find, you have, like, imagine you have an arithmetic function with arithmetic properties. It's not quite clear how you can write it as a sum of a certain coefficient times x to the power row. So we don't have, the one thing we're missing is that how to write, like, we know how to write primes. It's just like every coefficient is equal to 1, but we don't know how to write, like, for example, indicate a function of twin primes in terms of the zeros of the Riemann zeta function. It would be, like, pretty nice if you can find a formula for twin primes that you write it as a certain coefficient times x to the power row. What result next I'm going to show is, like, it's going to shed a little bit more light on this, and, like, it's a bit of a generalization of Landau-Gonnet formula. So when I was working on this, what I realized that if you take coefficient C of rho, you define it as, like, C of rho be a number of zeros that fall close to rho. And assume Riemann hypothesis, assume that all of them are in the half line. So, like, it's like the C of rho, like, looks very nice. Like, so C of rho would be like number of zeros are very close to rho. And imagine you use C of rho as a coefficient of x to the power rho. Basically, you create a sum like this. Then this formula, the support shifts from primes to product of two primes. So now, like, so one question can be answered is, like, how can I write the indicator's function of product of two primes in terms of x to the power zeros of Riemann zeta function? This is the way. But, like, I cannot say much more of, like, if you give me like a arithmetic function, like, best example would be like the twin primes, for example, indicator function of twin primes, or weighted indicator function of twin primes. I don't know how to write it. Like, if you give me some squares, like indicator function of squares, I don't know how to write it in terms of the zeros of the x, the variable of the function to the power zeros of the Riemann zeta function. It's an interesting question, and it's like, maybe there is some math above my grade there. There's a way algorithm to find this coefficient, but I don't know. So this is a point I want to make about justifying this. This sum I'm taking is a little bit look like that. If I'm taking a convolution of x power rho and a short interval around, and I, like, move this short interval around the imaginary axis. And on the right-hand side, the product of two primes basically is the convolution of Van Mangold function to itself, is non-zero if n is a product of two primes. So that's one way to explain it, and in one analysis way to explain it. So this is a theorem I proved. As you can see, this is, as I said, measures the number of zeros that are close to rho times x to the power rho. This is not very important. It's just a smooth way taking care of the range of summation. And as it's evident, and if x is equal to product of two prime, you get positive terms here. If x is primes, you also get positive. This is like when two primes are divided, you also have a positive contribution, but it's very small because if you have this q in the denominator, and the formula is equal to 0 otherwise. So it turns out that as you can see, I have x equal 1 for this. So it turns out that x equal 1 was a famous formula of Montgomery. Montgomery proved that if you assume the Riemann hypothesis, and like let gamma and gamma prime denote imaginary part of zeros of zeta, you take this sum, like look at it this way, that it measures a bit like how zeros can get close to each other. If gamma minus gamma prime is a small, you get a large value here, and if they're large, you get a small value. So Montgomery, it's just a famous theorem of his, which is a special case of the theorem I showed before my theorem. Montgomery, he proved this theorem when he was working on the pair correlation of the zeros of the Riemann zeta function. His motivation was like a very important problem in analytic number theory that many people tried and failed, is that it proved there's no Landau-Ziegler zeros. Landau-Ziegler zeros are not zeros of the Riemann zeta function. They're zeros of another L functions, but if they exist, they are, first of all, they're going to violate the generalized Riemann hypothesis that this family of L functions, all of their zeros are in the half line. So they are very bizarre zeros. They kind of fall even inside the zero free region for these L functions, and very close to 1 on the real line. If they exist, I mean, first point that is important is that they have important implication in algebraic number theory, proving that they don't exist, and class number formula. So yeah, let me say like what happened to Montgomery. Let me finish Montgomery's story. Montgomery, he was working on the pair correlation, motivated by proving that there is no Landau-Ziegler zeros. But the formula is not strong enough to prove that, to disprove it. What he does is that if you assume if you consider number of zeros of imaginary height is smaller than t, number of them you can easily compute about t times log t divided by 2 pi. From there, I'm trying to get that the average gap between zeros is about 2 pi divided by log t, and I'm talking about zeros around height t. So what Montgomery could prove was, assuming RH, he could prove that you get infinitely many gaps between consecutive zeros of Riemann zeta function, that they are smaller than 0.68 times the average gap. So it gets a little smaller than the average gap. The threshold is you want to prove that there are infinitely many gaps between zeros that are smaller than 0.5. So his result, if you look at this lim-inf, basically this lim-inf measures how small the gaps between zero can get. Montgomery's result gives mu smaller than 0.68. Toward the end of talk, I'll come back about other results in this problem. And most important thing is that if you can prove there are infinitely many gaps, that they are getting smaller than half of the average, then you can prove that there are no Landau-Ziegler zeros. It's obvious that if the Landau-Ziegler zero exists, they start to mess with the distribution of series of Riemann zeta function, which I'm going to get to later. Jesus. All right. So there was another, like this formula, like simple formula, I proved it. They had like lots of nice results came out of it. So he proved that at least 2/3 of zeros of like the Riemann zeta function are simple. Conjecture is that all of them are simple, but it's like there hasn't been much progress toward this conjecture. It seemed like a pretty hard, like it seemed something deeper than even Riemann hypothesis. So, if you notice in the theorem I proved, and I mentioned that the Montgomery result was a special case of it, I did not assume Riemann hypothesis. So, because of that, I could prove the Montgomery formula unconditionally. And I didn't need to assume the Riemann hypothesis. However, when the zeros are not in the half line, you get a little bit crazy terms here, and so you have to consider the whole zeros, and you have to consider a complex definition of the sine function. But the formula is more or less the same, just no Riemann hypothesis assumed. And because of that, because the problem is no longer depend on Riemann hypothesis, then I could get the corollary about the simple zeros under much milder condition than the Riemann hypothesis. So one common result was that if you assume Riemann hypothesis, 2/3 of zeros are simple. What we prove is that if you assume what is called zero density hypothesis, then at least 2/3 of zeros are simple. The zero density hypothesis basically allows you to have some violation to the Riemann hypothesis. Basically means that you can have some zeros off the critical line, but it says that the number of them shouldn't be too much. Going back to Landau-Ziegler zero, as I said, they are zeros for this L function. This comes from algebraic number theory. This is a character from a ZQ to C, and this L function, when the character is real, may have a zero, like very close to one, may have it. Everybody, like, I don't know, like, for a long time, many people believe that the Landau-Ziegler zeros cannot exist. Now, I guess some people, like, because it's been like so long, maybe some people, I'm hearing that some people say, oh, maybe they exist. Anyway, there is not that much reason behind like any of these speculations. So, but if they exist, they have crazy properties. So one thing they do, for example, if the Landau-Ziegler zero exists, you kind of can't prove the Riemann hypothesis, like at least a certain height. You can prove that if, for example, there's an exceptional zero for a character, for a L function attached to character of mod Q, then the zeros of Riemann Zeta function up to certain height, they all fall on the critical line. Another like funny like application is that if they exist, they prove the twin prime conjecture. They prove basically there's like an infinity many primes that they are like difference by 2. So this are result first by Hitz-Brown, and then I think a nicer exposition was with Friedlander and Iwaniak. But the most relevant thing they do is like relevant to what I'm going to talk about is what is so-called alternative hypothesis. In like an informal way, if they exist, they like seriously mess with the distribution of the zeros of Riemann Zeta function, or what is called perceived. So like Montgomery, when he was working on the per correlation, he came up with a conjecture. Conjecture is like, basically, you can look at it this way. It's like zeros of Riemann Zeta function are randomly distributed in a sense that you can get gap as a smaller than, gaps can get very small and get very large. Landau-Ziegler zeros, if they exist, they violate that. And so if I want to explain what alternative hypothesis, alternative to the prediction of Montgomery is that, so let's normalize them this way, that make the average gap equal to 1. Then this is a formulation from Farmer, Goenick, and Lee that I'm using here. It says that after a certain height, then the space between zeros, normalized space between zeros, are going to be just half integers. So basically they say that you're just going to have gaps of length 1/2, or 1, or 1.5, 2, etc. And this conjecture is basically made because of the possibility of Landau-Ziegler zeros. It's like a alternative to the Montgomery's prediction, which is called GUE. So what is alternative hypothesis means is like if G of sigma denote the portion of normalized gap that they are equal to sigma. Like for example, G of 0.5 would be the portion of normalized gap that are equal to 1/2. G of 1 would be portion that equal to 1. So after formulating the AH, they proved this, that if the alternative hypothesis is correct, then G of 0.5, and it means like the number of gaps that are equal to 1/2 is about 30% of the whole gap, not whole gaps between consecutive zeros. And the number of gaps that are equal to 1, it would be something between 40% and 50%. So I improved the result a little bit. I proved that the number of gaps that are like, if you assume alternate hypothesis, number of gap that is of length 1.5, it would be at least 10%. And it also gives upper bound for the rest of these the gaps of, so like gaps of length 2, 2.5, etc. And as you can see, the lower bound on the gaps of length 1.5, it depends on the gap, the portion of gaps equal to 1. So what does this mean? It's to explain it, I should talk about this. There's a recent result of tau, and independently was Logarithmic and Rogers. So what they did is like they construct a sequence that with alpha spacing equal to half integers that satisfy everything that Montgomery based his theory on. So he had like basically when Montgomery was making a conjecture about distribution per correlation of zeros, he based his condition on some estimates. So what they did is that they construct a sequence that is like the gaps in this sequence does not get small, and it's kind of very rigid. But they satisfy everything that Montgomery based his like model or his conjecture on. This is what Montgomery conjectured, is that if you have like kind of a weight function, nice weight function, and you imagine like this weight function, I don't know, support is like between 0 and epsilon. Like basically this side take care of the gaps that are getting smaller than epsilon. And it gives you in the right hand side, it gives you what portion of them like would be smaller than epsilon. What's important here is this kernel in the distribution function. This is the same for the distribution of eigenvalues of large matrices. And so because of this result, many people got very excited, and I thought that, so the Riemann Zeta function, it may be related to the spectral theory. And so if you, I don't know, if you study spectral theory, maybe you can find a way to prove the Riemann hypothesis, but there hasn't been much success in that direction either. And the result of a tau and Logarithmic and Rogers, it's kind of like a negative point for this whole like Montgomery's pair correlation conjecture, because so basically they construct a sequence that satisfy whatever he concretely had as facts, but they completely behave differently than what he predicted. So tau, he further proposed that it's like the alternate hypothesis. What he did is like maybe the correct way is alternative GUE. So alternative GUE is like, again, that the sequence of zeros, they satisfy this half integers property. But what he does, what his model gives exactly what portion equal to 1/2, what portion equal to 1, what portion equal to 1.5. This is what comes out of alternative GUE, which tau hypothesized. So it gives like around 30% would be gaps of length 1/2, about 45% gaps of length 1, about 20% the gaps would be 1.5. So how it relates to the theorem I had is like, so if we assume basically by the theorem I proved that if the number of gaps is as AGUE predict is 45%, then the rest of them they fall into the place. So this gives the 1.5 is about bigger than 20%, which is like his prediction is 20%. and like number of gaps of length 2 is smaller than 5%. Is like his prediction is about 4%, and that's basically sum up everything. So like the other gaps are going to be very small if you assume alternate hypothesis. So I think the important point is for years many people believe that the GUE is going to be the model that explain the distribution of percolation of like the series of Riemann Zeta function, but this recent results are like gonna like I don't know, put some doubt on it. And the one problem is that when you work on alternative hypotheses, you see that they show like a crazy consistency. They're like there's been a bunch of like different method developed, mostly by Montgomery, to study the gaps between zeros, and all of them the alternative hypotheses are kind of they resist all these methods. It's like this gap, like you can get close to proving that gaps are like smaller to 0.5 something, but you cannot beat that. So it's a little bit strange, and at the same time, it's like if the series of Riemann Zeta function are like even space or like kind of like all times rigidly spaced, people say, it doesn't make so like a violation, like with anything we have. So I don't know. It's like it's really the result of this tree is really added to the mystery. It didn't like solve much. So as I said, the mu measures that like the short gaps between zeros. I want to give a history of the result in this direction. This is the history is like Montgomery Odlyzko, like this is the method here is different than the method he had to study percorrelation. They proved that the gaps between zeros, consecutive zeros, they get smaller than 5179. Conry, Gosh, and Gonek, it's slightly improved at 5171. Then Bui, Milanovic, and Ing, they improved it to 5155. And Feng and Wu, the slight improvement. This is very small improvements. And the problem with the method, this is all results are based on the method developed by Montgomery Odlyzko. Problem with the method is like its method cannot beat 0.5. It even cannot beat 0.50001. There's an unpublished result of Goldstein that says that with this method, you cannot basically improve that bound. So basically means that this method is not useful for the application to the Landau-Ziegler zero problem. One explanation of this means maybe it can be, it's my speculation, that maybe like the majority of zeros, they are like more or less rigidly or evenly spaced, but once in a while you get zeros that are the gaps get close. And that explained that why they are like evading all these methods. But this thing I just said that it means that, so you have to do a little bit of surgery, maybe remove the evenly spaced zeros, then maybe you can prove the GUE, Montgomery's prediction, but it's just another speculation. Anyways, another result I have in this direction is that assume Riemann hypothesis, then the gaps between consecutive zeros either get smaller than 0.5, which is like the desired result for disproving Landau-Ziegler zeros, or the two consecutive gaps gets smaller than 1.18 times the average gap. So either you get like this nice result you want, or the two consecutive gap gets smaller. So this the result should be compared with the result of Conry and Butterbaugh, Turing Butterbaugh. They proved that two consecutive gap gets infinitely often smaller than 1.57 times the average gap. My theorem has 1.18. And that was the last result I want to talk about. Thank you very much for listening.
Okay, thank you very much, Farzad, for your great talk. Our audience may please unmute yourself so that we can all thank Farzad. If anyone in the audience has any questions, you may ask them.
I cannot hear anybody.
I have a quick question. A few slides ago on 32, I think.
32. Here? This one?
Yeah, is there a maybe short explanation of why the limit of Montgomery and Otley square approach is 0.5?
So what they do is they use a modifier. Modifier is like it's like a Dirichlet polynomial. Like just look at it as a function that it gets large value around zeros. For example, if you approximate 1 over Zeta of S, if you approximate it by a Dirichlet polynomial, you can make a modifier. Right? But length of this modifier is important in this for this application. So, so one important part of this story is that if the length of this modifier is a smaller certain threshold, you can like easily compute it on zeros. But if the length gets bigger than that threshold, then what some off-diagonal terms come in that you have to take care of. But for you to be able to take care of the off-diagonal terms, you have to assume like shallow conjecture with power saving. It's not just shallow, you need the power saving on. You also have to assume a conjecture about if you have a convolution of Van Mangold function and the Liouville function, and then you consider the shifted convolution of this complicated one, again with the Liouville function. It's like something, I don't know. I don't think anyone even made a conjecture on it. Maybe Simon made it. You have to assume the power saving on those two. Then you can get a longer Dirichlet polynomial, and you can prove that their gaps get smaller than 0.5. I did it with my supervisor in my PhD thesis. So why this result stop at 0.5 basically is that basically they in the heart of the result is the modifier of the length is smaller than threshold. And the Gaussian proof, if you get any modifier, imagine like the smallest modifier you can find of length is smaller than the threshold, you cannot beat 0.5, even slightly bigger than 0.5. It's pretty hard problems. In a way, it is deeper than Riemann hypothesis, because I mean, Riemann hypothesis says the zeros are on the half line. It doesn't talk much about how they're distributed. But it's like a problem that it has an important application in algebraic number theory. That's why many people tried it. But it's like there hasn't been any success, or any like say like this. There was this new idea that someone had to put. No one even had a good idea, I think, to look at this problem. Zhang has a manuscript on archive that he claims that he proved the Zigo-0 problem, but there's an error in it, and he hasn't retracted yet. Anyway, I hope it answers your question.
Thanks.
May I say something? Hi. There's a paper of Ivanets that gives.
Someone's talking.
Sorry, I think Farzad doesn't have your.
I can't hear. No.
Do you want to?
Hello.
Hello.
Oh, right. Sorry.
Yeah, Ivanets has a nice paper on this. Conversations about the exceptional character. It's in a Cambridge book.
Sorry, you got cut off again. Could you say it again?
Ivanets has a nice article about this. Conversations about the exceptional character. and gives some perspective about the relationship between the 0.5 barrier, and he says, like, no matter how they tried, they couldn't beat it, and there seems to be a conspiracy of the universe against it. I just want to make some people aware that there's an article like that, Conversations on the Exceptional Character by Ivanitz. Probably you know about this article.
I think I read it like a couple years ago.
Yeah. And the other thing I know of course, it doesn't disprove. There's someone called Beck, B-E-C-K, in Rutgers University, Joseph Beck. He has two articles about beating the Siegel barrier, like trying to turn it into some sort of effective estimate. The ineffective.
Oh, okay. The Siegel theorem. Okay, got it.
Yeah, the Siegel theorem. The first article is about some 30 or 50 pages. There's also a second article. I mean, this is a serious mathematician. He didn't publish. He put the first one in the archive, and if you're interested, you can get the second one from him. It's about 300 pages, though.
300 pages?
Yeah, but you could, I guess you can find it, I mean, in archive. Let me try to find it while I'm talking here. Beck. That's like, I gave some students to work on it, but they found after doing 20 pages or so, they went to different universities for...
They changed their major, huh?
Yeah, but the Joseph Beck was like, I'm trying to find it.
Sarnak called this exploration of this problem a disease. So you guys are working on the Ziegler zero is, you have a disease. And he was telling me this story that once he and Analytic, they thought that they broke it because they were relating the Ziegler zero to the half integral weight modular forms. And he was saying like maybe 4 months of work every day. They were talking, and I said, we really thought that we broke it. And at the end, again, we realized there's this exceptional character comes out into the picture that may have a zero very close to s equal 1, and basically coming back to square one. It's like this problem is very resistant to everything you throw at it. It's consistent with everything.
Yes, that's what Ivanitz says in his, that's like a survey article, Conversations on the Exceptional Character. But I can't find it because there's zillions of Beck in archive. Not all fields. How do we?
It's B-E-G?
E-E-C-K.
E-E-C-K.
Joseph. I wrote Joseph, but it didn't find it.
0, 0. No, I cannot find it on Go. Spectral zeta function. Is it? No, it's not Baker, is it?
No, not Baker. Beck.
Is it computing the continuous?
Is there an advanced search maybe I could do? Mathematics.
So this one. Why didn't it work?
Let's try it. No. It's not, I can't find it. I mean, I have the thing in my office, but maybe.
But if you find it, please send it to me. I take a look at it.
Yeah, it's an interesting work, but.
After the result of Tau and Lagarius and Rogers, I'm much more skeptical of, like, I think it's like it's really hard problem, and maybe Montgomery's it's not complete contradict. It's not a complete prediction that explained it.
They're being devil's advocate. Actually, it doesn't invalidate what Montgomery does. It's just
it does not.
It's just they're trying to say, like, such and such things happen, even if there's some other incredible behavior, which is okay. It's being devil's advocate there. I mean, the alternative hypothesis was also a devil's advocate kind of thing.
That's true.
But that's,
who came up with it first? Was it Hif-Brown?
Alternative hypothesis. I think it's in a paper of Farmer and Gonek.
No, because in my paper I attributed to them, and the editor was not happy and said it was Hif-Brown and Henry.
One student found this Beck article. Maybe I recommended it last year to them. Yeah, here.
Oh, I see it.
Now I will.
And you think there's a serious new idea in this paper?
Yeah.
Okay.
It's so that's the, yeah, it's a serious idea.
Mm-hmm.
I mean, it's been since 2013, and it's not been. So you got the paper, right?
I did, yeah. I'm looking at it.
And there's also a part 2, which is, this is 72 pages, by the way. I thought it was like 50 pages, but there's almost 300 pages of second article. But I guess he does this, the first page gives this effective estimates. Yeah, anyway. But
oh, so he just like he proves the lower bound on the L function at 1. Yeah.
Yeah, which
that works, yeah.
Equivalent to distance of the 0 from, you know, you can go from one to the other.
Yeah, I'm going to look at this. Thank you for mentioning it.
Yeah, it says he is a serious man. I mean, he's a serious mathematician, and he didn't submit it because 300 pages, nobody is going to referee it. So he was
he's confident.
Yeah, I didn't withdraw it. I mean, it's been there for 9 years now.
I mean, Zhang does not withdraw his paper.
Yeah.
Although, like lots of people I heard, they told him that because you're a famous person now, you should withdraw it. But he does not accept.
Yeah, there are people like that. There's also this other guy. What was his name? Japanese guy who claimed.
Oh, ABC?
Yeah, this.
Yeah.
I forgot his name now.
Mochizuki.
Yeah. Even when they find mistakes, they don't, or question him. They don't answer questions, or they don't withdraw the paper, and there are people like that.
Mm-hmm.
Maybe they think they still believe in their method, that even if there's a problem, it's fixable or something.
There was this joke, I don't know if you heard it. The ABC is a theorem in Japan and an open problem in the rest of the world.
Yeah, well. Yes. Anyway, nice talk. Thank you very much.
Thank you very much.
You want to talk?
So is there any other question? We just have one microphone. Do you want to get it?
Okay, sorry for the technical difficulty. So if the audience has any more questions, we ask. And if not, let's thank Farzad again for his great talk.
Thank you. Thank you.
Thank you very much, everyone, for coming, and thanks again, Farzad, for your fantastic talk. And we'll see you in 2 weeks.
All right. Bye. Bye, everybody.